Hello everyone, I'm going to share what I learned regarding the rough volatility and the Hurst component. These three colored lines, the pink, green, and the gold ones, uh, even before any explanation, you can already see that they look fundamentally different from each other. The pink one moves frantically and changes direction almost at every step. The green one shows moderate variation, and the gold one has a visible trends. This visual is the entire point of the presentation. Everything that follows explains exactly why they look different and why it matters. So, before we get to the math, we need a mental model. See, the roughness is fundamentally about what happens when you zoom in on a path. The smooth path, when you zoom in far enough, eventually it will start to look like a straight line with well-defined local direction. On the other hand, the rough path never does this. No matter how closely you zoom in, it will keep looking jagged, irregular, and chaotic. So, to put a number on this roughness, we use the Hurst exponent. It was originally developed by Harold Edwin Hurst when he was studying the Nile River flood cycles to measure the structural memory or persistence. The former mathematical definition states that um, for a process, the variance of its increments scales proportionally to the time window t raised to the power of 2h. So this is the scaling law. Notice that if we set the Hurst exponent to 0.5, the variance scales linearly to t, which is the standard Brownian motion. If the h is equal to 0.1, the variance scales very slowly, making the process highly constrained. And if it's 0.9, the variance scales rapidly, creating smooth trends. So a higher H, smooth trends, low H, we have high constraint, and if it's 0.5, it's the standard Brownian motion. Now, this slide here makes the interpretation of memory concrete. When H is 0.5, the process has no memory. Like a coin flip, the entire past history provides zero predictive power for the next step. If it's bigger than 0.5, the process is persistent, so positive autocorrelation means the influence of the past trends decays slowly, and momentum feeds momentum, much like let's say stretch rubber band. When it's less than 0.5, the process is anti-persistent, so it actively fights its past rapid spikes immediately collapse, acting like a tightly coiled spring that violently mean reverts. This table is a reference, let's say, for the three regimes of path personality. When H, let's say, rough 0.1, the paths oscillate frantically with strongly negative autocorrelation, precisely matching the behavior of realized volatility and steep short-dated skew. Though a perfect hedge becomes impossible when H is 0.5, so random, The paths have moderate variation and zero memory, representing like the black shows the stock prices where perfect delta hedging works. But it incorrectly flattens out the volatility smile. But when it's smooth, so H 0.9, the paths show visible momentum and positive autocorrelation. Now to formalize this roughness, using the fractional Brownian motion, so FBM. It is a unique Gaussian process defined by key properties. The first is the self-similarity. Rescaled segments are statistically identical to the whole, forming a fractal geometry. The second is the stationarity increments, meaning the degree of roughness is uniformly constant across time. The third is the Holder continuity, meaning paths are continuous but strictly irregular, with H perfectly controlling the path regularity. Fourth, the H bigger than 0.5, autocorrelation decay hyperbolically, exhibiting long-range dependence. Most critically, for H different than 0.5, it's not semi-martingale, meaning the classical calculus fundamentally breaks. This is an important remark. So the fact that rough paths are not like fundamentally break the calculus is a massive mathematical barrier, because we can't write a standard Ito integral for the fractional Brownian motion. Ito stochastic calculus, like the entire foundation of classical derivatives pricing, is voided here. So there is no straightforward replication argument, no simple delta hedge, and the classical Black-Scholes derivation simply does not apply. So we cannot ignore roughness. It forces the quantitative finance industry to abandon traditional models and rebuild pricing from scratch. So why would you go through all this trouble? Because of an empirical crisis hiding in the options market. Traditional models, as we said, assume H 0.5, but they fundamentally fail to replicate the extreme steepness of the short-dated implied volatility, or the volatility skew. If you try to fit them to the market data, they flatten out incorrectly. So the rough volatility was actually discovered by looking directly at the market data that classical models cannot explain. So rough models naturally generate this exact steep short-dated skew. So to prove that the volatility is rough, we must extract its scaling signature from market data. Step 1 is proxying volatility. Since true volatility is unobservable, we use the natural logarithm of ultra-high frequency realized volatility, so the log. Step 2 is calculating the structure function. So quantitative analysts or quants calculate the empirical moments, so the averages of the absolute difference in this log volatility across various time lags. If volatility is fractional, it will mathematically follow a strict power law. So to uncover this Hurst exponent from that power law, we use the logarithms by applying logs to both sides. The power law turns into a simple linear equation. So this log is equal to this log, which is slope plus a constant. This is exactly like this equation of a straight line that we know, where the log of the moments is on the y-axis and the log of the time is on the x-axis, and the slope is qh. By setting q equal to look at the variance of the increments, the slope of the line equals 2h, allowing us to easily calculate h. So when researchers run this log-log regression across real market data, the empirical truth is undeniable. They found that the volatility is fundamentally rough. So the data points from a near perfect straight line across thousands of assets, including equities, indices, commodities, forex, foreign currencies. Regardless of the asset class, the slope consistently yields a Hurst component of almost 0.1. This is not noise. This linear scaling on a log-log plot is the definitive empirical proof that the pre-models where they assumed that the H 0.5 were structurally wrong. So this is where the volatility the theory translates into the rough Burgomi model. The equation defines Vt, the instantaneous variance at time t. It evolves starting from the forward variance curve, which automatically calibrates to today's market expectation, read directly from the variance swaps. This is driven by the Rough engine, a fractional Brownian motion, injecting the h equal 0.1. It also incorporates the volatility of volatility and centering drift term, ensuring the expected variance equals this one. So the elegance of this rough Burgomi model lies in its parsimony and precision at the microscopic scale. First, structural skew. By naturally injecting H 0.1, the model perfectly matches the extreme short-dated option skew without introducing artificial jumps. Second, forward initialization. By starting here, the model natively respects the current term structure of variance swaps, requiring no secondary fitting. Third, extreme parsimony. It requires only 3 parameters to calibrate. So the H roughness and this one, the volatility of volatility, and the correlation, making it fundamentally immune to overfitting. However, there is a computational bottleneck or wall because the fractional Volterra kernel is not semi-martingale. As we said, the model has no closed form solution, so every single option price requires heavy Monte Carlo simulations, turning calibration into a bottleneck that takes hours, rendering it useless for live trading. The solution forward is clear. We acknowledge that roughness forces the industry to adopt machine learning to fasten this bottleneck, because deep neural networks can map parameters directly to volatilities, entirely bypassing the Monte Carlo simulations. So to synthesize the rough paradigm, we have 6 core takeaways. 1. Zoom invariance. Roughness is fractal property. Paths remain jagged at every microscopic timescale, so no matter how much we zoom in. Second, memory is structural. So the Earth's exponent dictates path momentum, and real markets exhibit severe anti-persistence. Third, the fractional Brownian motion formalizes it, so it provides the strict calculus required to model non-standard memory. Fourth, the universal 0.1, because empirical log-log regression strictly proves real volatility lives at h equal to 0.1. 5. Fixing this skew. The rough Bergomi model utilizes this math to perfectly replicate short-dated market realities. 6 is the AI imperative. Broken classical calculus leads us to forces us to use neural networks calibration for real world application. This is a small simple notebook to try and build a single control visualization that answers what does changing the Hurst exponent actually looks like on a path. So what we're going to do is we simulate 3 fractional Brownian motion paths, one for each of the h 0, 1, 0, 5, and 0, 9, and plot them side by side. And then crucially, all these 3 paths share the same underlying random seed, because we will generate random numbers, meaning every visual difference is caused exclusively by the value of h, not the data itself. So by the end, you'll have built an intuition for how 0.1 produces the jagged rapidly oscillating path that matches realized volatility data. The 0.5 is the standard Brownian motion, or the Black-Scholes assumption, and 0.9 is the produces the smoother trending behavior. So we need this math background. You can read this for the zero mean covariance structure and the self-similarity with the index h. So and the parameters is the Hurst component, etc., etc. So we will use this method to simulate the fractional Brownian motion. So the idea is to build the n by n covariance matrix using the covariance formula here, and then we will compute the Kolsky factorization, generate a random normal vector. The product gives you a sample with this distribution, which is an exact FBN sample. This method is exact, so not an approximation, and straightforward implementation with NumPy and SciPy. So the only limitation is memory. The covariance n squared is n squared, so for large n it becomes expensive. We'll start by importing the libraries. We will use this one, as we said, the Kolsky decomposition, because it's more robust than linear algebra Kolsky for near singular matrices, which can occur at extreme h values. And then we will set the parameters dc, dn, dh, dt, etc. Set up some colors, labels. So we will have 800 by 800 elements, which is this number. And then this is the covariance function for the FBM. We will do this in this function, and then we return this sigma, and then we will have a sanity check where we will verify that the h is 0.5. It would minimize the ti and the tj. Next, we will build the FBM simulator under the Kolsky method. So we will build the sigma, so the covariance from this step on the time grid, and then decompose it, do transform to standard normal, and then prepend the zeros because the FBM starts at 0 by definition. So we are going to do that and make a simple test to simulate one path and print the basic statistics, and then we'll simply simulate the other, or the three paths in the case of 0.1, 0.5, and 0.9. Next, we're going to compute and display the autocorrelation increments. So we expect at 0.1 we will have a negative increment, so negative correlation here, almost zero, and here a big correlation. And now we will do the main visualization. This is it. So we can see at h equals 0.1 it's rough, and like we have many fluctuations. At 0.5 for the memoryless, or the under the Black-Scholes assumption, and this is smoother, more like trend following. And next we will zoom to see what we and to check what we will see. So after zooming, you can see this nice visualization. Like even after we zoom in the first one, it's still jagged. We have many fluctuations here. In the second one, it's like we have the similar variation. So this one is similar to this one, and here it's when you zoom in here, we can see that it's smoother, like almost linear. And now we will perform step 9, which is variance scaling, to verify the fundamental Markov property of the power law, because the scaling law is both the definition of the h and the method used to estimate h from real volatility data. So the structure function method is described in the slide 7 of our presentation. So if you understand this plot, you will understand how the paper proved that h is almost equal to 0.1 for realized volatility. So this is the computation. You can see the key parameters, and this is the plot. So yeah, that's it. Let's summarize and see the key takeaways. We said that the fractional Brownian motion is parameterized by the Hurst exponent. The three cases, less and equal and greater than 0.5. Also, there is self-similarity. Next, we saw the variance scaling law. when we had the slope, like for the log-log scaling plot here. So everything in this notebook is just preparation for the rough Burgon model, where variance is driven by by the Hurst exponent. So every visual property observed is what drives variance in the model.